Now, as you might have noticed, one of the problems when we get to these larger atoms is it gets kind of a pain. Let's look back at these electrons. When atoms come near each other, imagine when atoms react, from a very crude standpoint, you've got the nucleus of one atom, the nucleus of the other atom. All these electrons out here spread out, however they are, in all these orbitals, whatever shape they're in. It's really only the outer electrons that we care about, because those are the ones that other atoms encounter. It's the outer electrons that are involved in bonding, so we don't really care about the inner electrons. We've already mentioned that noble gases don't bond or almost never react, so it ends up that the electrons in noble gas configurations don't participate in bonding. So we only care about the outer electrons. So down here with chromium, for example, if you look at the periodic table, you'll see that the argon has 18 electrons in it. So these electrons have the same configuration as argon. Those electrons are in a nice stable configuration and aren't going to change anything. They're not going to participate in bonding. So instead of writing all these electrons out, we really only care about these outer electrons. So we use what's called a noble gas shorthand, noble gas configuration, to abbreviate, just to make it easier to write. And as this is showing, the noble gas configuration is a shorthand, and it only shows the outer electrons. So we put brackets around the noble gas to represent the configuration of that gas. So for example, brackets around argon, as we just said, represents 1s squared, 2s squared, 2p6, 3s squared, 3p6. This is the configuration for argon. Now, brackets around argon is not the same as argon. It just means I've got 18 electrons. So we can abbreviate these elements, these configurations, as noble gas configuration. Take the previous noble gas, look at sulfur on the periodic table. The previous noble gas before sulfur is neon. So we can represent this as neon, which represents those 10 electrons, 3s squared, 3p4, which is easier to write. For scandium, the previous noble gas before scandium is argon. So as we said, this is these 18 electrons. So instead of writing all those electrons out, we can just put argon, 4s squared, 3d1. Or down here for chromium, same thing. Take these previous 18 electrons. We're at argon, 4s1, 3d5. So it makes it a lot simpler because it's really only these outer electrons that we care about. Take something like, let's do one a little bit trickier now. Let's take something like tungsten. If you look at tungsten, we have 74 electrons. Just to keep that in mind. We start with the previous noble gas. Go back from tungsten, look back to the previous noble gas is xenon. So instead of writing out all those, 54 electrons, we can write xenon. Then we go down to the next period. It's the 6s row in the s block, so it's going to be the 6s. So it'll be 6s squared. The next space is actually in the D section, so count down from the D's. 3, 4, 5 is going to be 5D. It's going to be 5D1. Follow the atomic number. Now we go down to the F. We're in the first F row, so that's going to be the 4F. And that gets filled up completely. We go across the entire row of F's, so it's 4F14. Now we go back up to the D. You look at tungsten, it's got 3 more electrons in the D. It's a total of 4 electrons in the D, so we put 3D4, change this 1 to a 4. And that's our configuration for tungsten. Now, a couple things here. The first is be careful about counting up electrons. I'd always double check at the end. Xenon has 54 electrons. I've added 2, 4, 6. I've added 20 electrons to give me a total of 74 electrons by my configuration here. I've added up all these to get 74 electrons. I look at tungsten again. It should have 74 electrons. That's a very good way to double check. The other thing I want to mention is the way we write configurations. I'll accept things in different ways. I'm not picky about the order. One thing you should not do here, even if you filled them up this way, is 6s squared 5d4. I'm sorry. What we fill this up, to go back, is we put in the 5d1, 4f14, then we went back up to the 5d and put 3 more electrons in it. But this is not proper. It's more confusing. The d should all be combined together as the 5d4, as I wrote up top, versus having, you don't want to split up an orbital into 2 different sections, or not an orbital, you don't want to split up a subshell into 2 different sections. And you also need to be aware that these can be written different ways. Text will often, and some people are more picky about this, in putting orbitals in the energy level when we fill them up. So after you rearrange them, the proper way to write this is really 4f14, 5d3, 6s squared, having the lowest energy level listed first and higher and so on. That's more proper. I accept either way. I'm not very picky about it. Because in some ways, having the one you filled in last at the end, like up here, really makes sense, because in general, that's ones that you may lose first, but not always the case, and we'll discuss that in a bit. But that should give you a little bit of a heads up on electron configurations and the noble gas notation. Now, another way that we often write the electron configurations is what's called orbital notation, or orbital diagrams. And in this case, we actually show the individual orbitals. As it says here, we use either boxes, lines, or circles to show the individual orbitals in a given atom, or ion for that matter. Normally we show orbitals only of the outer subshells, because again, those are the ones we care about as far as bonding goes, or as far as paramagnetic, diamagnetic properties. Whether atoms are repelled or attracted by magnetic fields depends on really the number of electrons that are not paired up, that occupy, or the number of orbitals that have lone electrons in them. And a few things to keep in mind, this helps us understand a bit more about how electrons are filling up these subshells, is we place 1 electron per orbital in a given subshell first before pairing up any of these electrons. Because again, orbitals, electrons repel each other, so they want to be away from other electrons if they can be. All single electrons have to have the same spin. That has to do with magnetic fields that they're creating. It's more stable if their magnetic fields are all lined up in the same direction. It just makes the atom more stable that way. And any pair electrons have to have opposite spins. That makes them more stable within that given orbital. Otherwise, if they have the same spin, they actually have too much repulsive effect when they're stuck together in that tight space of that one orbital, that single orbital. So they have to have opposite spins. A few examples of this, just to show you, and I'll work some out to help you see it a little bit better. We can use, again, either in this case, either squares, I've seen circles, or just use a line to represent each individual orbital. A hydrogen atom has 1 orbital, so it's the 1s. And we denote the electron using an arrow. This is an arrow up to represent an electron with an up spin. For helium, we have to have 2 electrons in the 1s, so they have to have opposite spins. And you keep going, and this just shows more examples. You look to this as a reference. I think, go back there. I'm going to work through a few examples for you. I think it'll make more sense that way. Redo a couple of them we looked at. Let's look at, let's say, do something simple first, say something like boron. I'll write the configuration of it first. Again, do this yourself for practice. You should have a handle on this by now, I hope. 1s squared, 2s squared, and 2p1. Those are the 5 electrons in a boron atom. So for the orbital notation, we tend to not worry about the inner electrons. In this case, the electrons that have the noble gas configuration. So I usually specify only the outer electrons, but if you want to be, we could say like helium electrons, and then show the orbitals for the 2s. I tend to draw them like this. Again, you can use a box or a circle if you want to. And then for the 2p, I often use 3 lines, or you can use 3 boxes again. Doesn't really matter. easier to draw a line. But anyway, so we have 5 electrons to place. We'll fill up the first orbital first, this first subshell. So the 1s is filled up with these 2 electrons. Those are already used. So I need to go to the 2s. 1 electron up, 1 electron down. It doesn't matter in which direction the first electron goes. It could be up or down. It's actually all relative. Now I put 1 electron in the 2p, so I put, an electron spin going up, and that's it. This is my orbital notation. It shows that in the helium atom, in the boron atom, I've got actually a total of 1 electron that is unpaired. Right down here. And I actually have 4 paired electrons total. Remember, I've got these 2, but I've also have the 2 in the 1s. Can't forget about that. And now let's look at oxygen for a better example. Again, our electron configuration is 1s squared, 2s squared, 2p4, and so if you want to put the 1s, that's fine. If you want, we can do this 2s and the 2p. I just want to use lines in this case because it's easier, right? The same thing. Again, the 1s, we could just put helium notation or shorthand for noble gas notation instead in most cases. So these electrons need to be paired up. For the 2s, the same thing. 1 electron here, 1 electron here. So for the s's, it's easy to see. We just have to stick electrons in opposite spin. For the p's, this is where the other rules come into play. So keep in mind, all of these 3 energy levels, all these 3 orbitals have identical energy states. They're the same energy. When I put an electron here in this orbital, the next electron, if I put it over here with this first electron, they're in the same orbital. They repel each other because they're negative charges. So it would rather be over here by itself, where there are no other electrons nearby in this orbital. And this third electron would need to be over here. Again, they have the same spin because that lines up their magnetic field, so it makes them more stable than opposite spins. And again, it doesn't matter if they're all 3 spin up or spin down, as long as they're all the same spin. And now I need to put in my 4th electron. Now we have to pair up electrons, so I'll put it with one of these, doesn't matter which one. So I have now 2 unpaired, electrons, and I've got 6 paired electrons. So this helps us understand a little bit better about whenever atoms bond. You can see the unpaired electrons. Whenever we look at reactivities, we care about these outer electrons. Later in 105, you look at hybrid orbitals, and you need to understand this configuration to understand where the hybrid orbitals come from. So this again gives you a little better physical image of what the orbitals look like when we look at the periodic table. The p sublevel, like the 2p, is 6 bases wide, but that's represented by 3 orbitals. Remember, the 3 p lobes, one is on the x, y, and z axes, and so these electrons are lined up in one of those 3 orbitals. As far as, let me try to get that. One thing I want to show you as far as the oxygen also, you might see sometimes it written this way. Or with any p for that matter. 2px, 2py, 2pz. It'll be the same thing up here. Oh, I don't know what I'm doing over there. I'm getting happy with my electrons. Sorry. Alright, that's better. I just want to point out that sometimes you'll see the individual orbitals in a subshell being labeled. 2px, 2py, 2pz denotes the individual p's and those individual axes. You will never have this with the s because there's just one s in a sublevel. With the d's and f's, you might see them labeled sometimes. The x and xx, xy, they're more funky labels. But just don't be worried about those. It's just labeling individual orbitals in a sublevel. For what we do, it doesn't really matter. For certain types of spectroscopy, it can make a difference. but just should be aware that we have different ways we can label those guys. Even something looking at something like orbital notation for an iron atom. Well, you can write out the configuration yourself first, I think, for practice. We want to pause the video and do that, and then I'll go through a little bit briefer description of that. All right, the previous noble gas is argon, so I'm just going to put down argon in brackets again. I want to point out that argon in brackets just means I've got 18 electrons in this configuration. It doesn't mean that I've got an argon atom. And now I'll go after argon. I've got the next period, so I'm going to have my 4s orbital, and then of course my 3d. For iron, we've got 2 electrons here. We've got, of course, if you count, 6 in the 3d, so we put 1 electron in each orbital, and we pair up 1 to get our total number of electrons. Again, double check. We've got 18 electrons here, 19, 20, 21, 22, 3, 4, 5, 26 electrons total. Iron has 26 electrons, so that's a good way to double check. I think it helps to look at, as far as exceptions to the octet rule, I want to do, you can do the same thing with chromium. I want to look at copper, to show you copper. Again, it'll be the same thing. (4s) and the 3d. 4s has 2 electrons, the 3d has 1, 2, 3, 4, 5, 6, 7, 8. That's the expected configuration for copper. But over here we've got this orbital over here that has 1 electron in it. It makes this whole d subshell kind of asymmetric. It ends up in what happens in many cases. You can see this goes from the 4s loses an electron. The 3d ends up being fully filled. And that makes this entire configuration a little bit more stable. Or like we did earlier with the chromium, I'll go ahead and show you this now. Let's go down here. I'll make sure you got that, looked at that thoroughly. Again, having a half-filled subshell is often preferable to having this other fraction, since the 4s and the 3d are at very, very similar energy states. So if we go to, if you haven't done it yourself, recommend look at chromium here just to show you the exceptions and for the electronic configurations. Again, we said it has 24 electrons, so argon, we expect it to be 4s with 2 electrons, and then the 3d. So here you can see we've got, it's probably easier to see here while we have the exception. In the 4s, we've got 2 electrons packed together in that same orbital. Well, again, they want to be near the atom because of the nucleus, the protons are attracting them, but electrons repel each other. So one of these guys says, well, hey, this guy has very similar energy over here, so let me just hop over there instead. And so we end up getting all these, in this case, these 4s and 3d orbitals are very similar energy states, I should say, even though they're different energy levels. And this ends up being more stable because every electron is by itself, is farther away from other electrons, farther away from other negative charges, and it makes it more stable. And this also leads to, again, as I was saying earlier, orbitals are kind of dynamic. They change their energy states up and down as you add electrons to them. So things don't always go as we expect. If you take something like, let's go back up here, even with iron, we fill up, go back over, we fill up the 4s before we fill up the 3d. With many transition metals, so what happens is, whenever as we fill them up, we add in the 18 argon electrons, we start adding more electrons in, this 4s gets filled up first, then the 3d, except once we get these guys with all the electrons in them, the energy shifted some, and it ends up that the 4s is at a slightly higher energy state than the 3d. So these electrons also are the electrons that are lost first as we form ions, or as we kick electrons off. So they get lost first, and then the d's get lost later. So you get some weird things happening as we add electrons to these orbitals. So just to give you a little bit of a feel again for what happens with these guys.